All right, so these are going to be the guided notes for section 2.4. I'm going to make a video for the first page and a video for the second page, and when we come in class next time, we're going to work on the third page. So we've already talked about the answer to these first few things. This is write the definition of the formula of the average rate of change below. So the average rate of change, of course, is the slope between 2 points on a graph. So you should already have that in your notes. And then the mathematical definition is it's f of b minus f of a over b minus a, right? And again, that's the slope between 2 points on the graph of a function. And we called the line that passed between those 2 points the secant line. So the arc is the slope of a secant line passing through a function at any 2 points. So picture that, here's a function, it's the same one I drew on the board. Here's the 2 points, b comma f of a, b comma f of b, and then a secant line is the line that passes between those 2 points, and the slope of that is the arc. Now, that's one type of rate of change, and that you could have done in Algebra 1, Algebra 2, but what makes calculus unique is instead of thinking about a rate of change over an interval, like a change in y and a change in x, even though I just reversed those, we want to talk about sometimes what the change is at a particular instant. So the rate of change that we're really going to be interested in this section is something called the instantaneous rate of change. That is going to be abbreviated as the IROC. And an instantaneous rate of change measures the rate of change, how quickly something is changing at an instant. So let's just say it's the rate of change at a particular instant. Now, what I'm going to draw here is just sort of an illustration of how we deal with an instantaneous rate of change, and then don't write this down unless you just want to, but then I'm going to draw at the end a representation of what the IROC actually looks like. So if we had a graph and we were talking about an AROC, the slope of a secant line, the way we would find an instantaneous rate of change at, say, a point like this, is we would think about finding AROCs over smaller and smaller and smaller intervals, with the idea being that if we can make the interval between the points that we're finding the slope really, really tiny, it's almost like measuring the change, the change at that instant. So we would really like to make those points as close as we possibly can to each other. But we can't let them touch each other, because as soon as we let them touch each other, our slope becomes 0 over 0. And that, of course, is undefined. So the idea is we would like to let this point right here get closer and closer to this point right here. This is going to lead us to 2 mathematical definitions of the IROC. So I want to show you in pictures what each of these look like. All right, so the first one is I have 2 points, and one of my points is going to be fixed, meaning it's not going to move. That's going to be the place where I want to find the IROC. So whenever you have fixed points in math, you tend to represent those with letters from the beginning of the alphabet. Oops, sorry, that's supposed to be an A. But this other point, this one right here, we want to move. We want to slide closer and closer to this point. And whenever you have points that want to change, those are called variables. So we tend to represent those with letters at the end of the alphabet. So I'm going to call this one x, f of x. And what we're going to do is we're going to do something with these graphs, basically these points, basically to move them closer to each other. So the way we're going to do that is we're going to take the x value at which we have this point, And we're going to move that x value closer and closer to a. The idea being that we are building intervals that are smaller and smaller, so the instantaneous rate of change is getting closer, average rate of change is getting closer and closer to the instantaneous rate of change. So it looks like that, and then like this, and then like this, and then like that. But we can't let them land on top of each other. So essentially what we got then is we are finding a slope between those points, which would be f of x minus f of a over x minus a. That is the a rock, but in order to make it an I rock, we want those things to get as close to each other as possible without actually touching. And we want that x to get super close to a. And the way we do that is using a limit. And that's why we needed the limits in the first place. So this is one definition of the I rock. This is called the A definition for obvious reasons. Now, the other definition is a little bit harder to see, but it works much the same way. So I'm going to draw a little set of axes for this. So draw a function again. Got my fixed point here, which is still a comma f of a. But this time, instead of thinking of that other point as being a different value of x, what I'm going to think of is how far do I have to move over to get to that x value? So instead of it thinking of being like, here's an x value, here's an a value, we're going to think of it in terms of this is just an x value, the fixed point, and then this is a change in x. And we would always label a change in x as delta x, right? So if I think of it that way, my new point started at a, and I added a delta x to it. And then to get the y value there, I would plug that number into the function. Now, we still want to find the slope between those things. So that would be change in y. Over change in x, which by the way, you could write that as a plus delta x minus a, and that would still give you delta x. And we would like those to get closer and closer and closer to each other. Well, if we slid these x values closer and closer to each other, what's really happening is this delta x is getting tinier and tinier and tinier. So the limit we're going to write out here is going to be the limit as delta x approaches 0. Now, this is a fine way of writing this, and oftentimes you'll see this written and used. The biggest problem is that delta x is a two-symbol variable. Basically, it's two things that represent one change, right? So a lot of times you'll see this written where the delta x is replaced with a single letter just to make it easier to keep up with. And the letter that's typically chosen is h. So delta x is exactly the same thing as h. They are synonymous with each other. This is the form we will be using most often, and this is called the h definition of the I rock. Now, one last thing I didn't add. So you notice up here, when we were talking about drawing the picture, how if I drew the points closer and closer to each other, the line started getting less and less secant and started looking like it would eventually touch the graph at one point. Well, the I rock, while the A rock is the slope of a secant line, a line which passes through the graph at 2 points, the I rock is the slope of a tangent line, which touches the graph at a point. So if I did the slope of a tangent line, that is the I rock. And that's what we're going to be finding using these definitions. So in the next video, I will walk you through some examples of that.